Hello. Okay.
And so the next talk by Vladimir from Universidade Federal Fluminense, among other affiliations that he's not putting there.
Okay. So thank you for the introduction, and thank you also for the organizing for the opportunity to show some of our work. This work was performed in collaboration with Caio Levenkoff from Universidade Federal Fluminense and Eduardo Muciolo from University of Central Florida. The outline of the presentation is displayed here. I'll talk very fast about spin relaxation in graphene, just summarize some of the discussions we already had during the week. What's different about the spin relaxation here, the origin of the puzzle between the fast spin relaxation observed in experiments in comparison with theoretical prediction, the origin of carbon magnetism due to defects in graphene, and the mechanism of spin flip hotspots for spin relaxation in graphene, and then talk about our approach to derive spin relaxation times in graphene, and discuss some of our results. So, as already discussed in our previous tutorials, what is different about spin relaxation in graphene is the fact that the material presents very low spin-orb coupling, about the order of 10 microelectron volts, which was predicted due to this fact. Theorists predicted that spin relaxation due to the usual mechanisms of Elliott-Jaffet and Diakonov-Perel will lead to spin relaxation of the order of 1 microsecond in graphene, which is orders of magnitude larger than other conventional materials. Now, when we came to the real world and the first experiment was conducted, when the spin relaxation times were extracted, they were observed to be of 100 picoseconds, about 4 orders of magnitude smaller than predicted in the theory. After that, several other experiments have been conducted on top of different substrates of different qualities, and the spin relaxation times measured were also still at most 2 orders of magnitude lower than predicted by the theory. Then theorists have proposed several mechanisms to explain the origin of the fast spin relaxations in graphene. I will only approach one of those, which is the spin relaxation due to spin flip hotspots that was developed by Denis Koshan, Martin Dimitra, and Jaroslav Fabian. So before I continue, there's a few comments about the defects we consider that lead the magnetism in graphene, which are hydrogen and vacancy. In principle, nor hydrogen nor carbon are magnetic materials, and it's not expected that the addition of a hydrogen atom on top of a carbon atom, or the remotion of a carbon atom from the graphene layers, would lead to a magnetism. However, due to a theorem by Lieb, it can be shown that for those bipartite lattice, every time you create an imbalance between carbon atoms of the sublattice A and B, you will have a ground state with a magnetic, you have a magnetic ground state system. The theorem only tells about the overall system, but recently the local picture has been derived by DFT studies, which shows also another unusual character of this pi-like magnetism, which is the extended character of the induced magnetism along several carbon atoms of the lattice. And this was recently also measured experimentally by STEM studies on graphene with hydrogen and graphene with vacancies, and also this extended magnetic texture was observed in the experiments. Okay, now going back to the spin relaxation experiments, as Roland talked a little during his tutorial, they performed experiments on hydrogenated graphene and graphene with vacancies, and observed that the effects of such impurities on the non-local resistance was the appearance of such dip in the system, which they attributed to exchange magnetic fields generated by those impurities, and a similar result observed for vacancies and hydrogen, which they stated that this should be occurring due to the pi-induced magnetism. Another intriguing result was due to the group of Bart van Wes, which observed that upon hydrogenating graphene, the spin relaxation times actually increased, which would be expected to decrease with the hydrogenation. Well, inspired by those results, this proposal of magnetic impurities in graphene as a generator of the spin relaxation was conducted by Dennis Caution, and they were able well, the mechanism essentially attributes the spin relaxation to the exchange coupling between the conduction electrons and the magnetic impurity, and in their results, they were able to fit the theory with the experimental results of hydrogenated graphene by Bart van Wes. After that preliminary work, several other proposals of spin relaxation in hydrogenated graphene have been performed, and as you can see, the theories use different mechanisms to try to fit the experimental data, and it's not clear what is the effect of such different mechanisms. For instance, in this approach by Caution, he uses the magnetism and also temperature and the effect of puddles, different concentrations. In some studies, models of vacancies used, in others for hydrogen. And our idea was then to try to clarify a bit what are the impact of those different mechanisms for the spin relaxation. So we actually have been working previously on the problems related to magnetism due to vacancies in graphene, where we have performed a study to estimate the charging energy of the vacancies, and another one which will be useful for this work, where we develop an Anderson impurity model for graphene with puddles and would study the Kondo effect. So the same model will be applied here. The essential idea is to start from the tight binding for the defect model, a vacancy or hydrogen atom. The vacancies represented here only by the turning off the hopping between the vacancy site and the neighbor sites, and the adatom is represented by the inclusion of on-site energy of the adatom and the hopping between the adatom and the carbon atom. Now, once you solve this Hamiltonian, you get these states, a set of extended states and one mid-gap localized states, and these will be the ingredients that will be used to construct our Anderson-like model, following the correlation between these localized states and the one observed for the impurities induced by the experiment. So the idea is essentially try to rewrite our Hamiltonian with an Anderson-like form, but if we try to do that immediately from this base, we won't have the coupling term. Since the basis is orthogonal, it's a non-trivial, it's a trivial result. However, if you remember that in graphene, we also have the effect of puddles in the system, which we can manage to create an Anderson model by including the long-range disorder term in our modeling. So the long-range disorder term is modeled by this term here, which was also discussed previously, and we will, in our simulations, adopt parameters for realistic systems as HBN and SEO2. Now, if we return to our projective algebra, what's important here is that our impurity term is given by the mid-gap states, and the energies of this impurity will fluctuate with the disorder realization. For our coupling term, we have a band term, which will also depend on the disorder, and a coupling term for which the coupling between the impurity and the band will depend on the strength of the disorder potential. Moving back to a second quantization formalism, we can recast our Hamiltonian as in this more traditional Anderson-like picture, where the last element for the model is a charge in Coulomb energy that we will leave as a free parameter here, but we also performed an experiment in which we detailed explain how to calculate this. So the last step for the formalism is one should keep in mind that the Anderson model can present not only magnetic states but also a non-magnetic phase. Since we are interested in the spin flip due to the magnetic states, we need to perform a Schrieffer-Volz transformation to extract the magnetic regime of the system. This is what we do here. And the only important thing for you to keep in mind is that the exchange coupling will depend on the energy, and also that the energy of the band states and the impurity states can be of comparable order here, which is not usual in other systems as metals. And this has an important impact on the results you derive. The last steps, the derivation of the spin relaxation times. For this, we use the Fermi Golden Rule approach, where the transition probabilities essentially depend on the coupling between the states beta and beta prime. And then we can define a relaxation rate for a given state beta, which is the contribution of all the states beta prime transitioning to state beta. Similarly, you can define a spin relaxation time for a given energy epsilon, okay, by summing over all the energies, the relaxation times with energy epsilon, and also evaluate the effect of different configurations for the disorder by averaging over different disorder configurations. So our first results obtained for vacancies here are not very enlightening, since we observe the exponential decay dependence of the spin relaxation time with energy, which is not consistent with the experiment, also for HBN and for SeO2. And we discovered that this behavior was related to the fact that the hopping between the band states and the impurity also were displaying this exponential behavior with energy. Well, we then made an approach to try to connect our modeling with the experimental scenario, where actually the impurity, the magnetic impurity only extends over a limit of almost 2 nanometers away from the defect. So our idea was to modify our impurity to a radius r around the defect, and when we do that, the R's I will present were about 1 angstrom, which confine the impurities those sites, and to 2 nanometers. We observe that the exponential dependence of the hoppings vanishes. Now, when we come back to our calculations, our relaxation times, we have a very different picture, where we can see, the first thing that we can see is that the dependence of the mean relaxation times, the red and black curves here, don't vary very significant according to the values of the radius we used, and this suggests that the previous models that used more confined magnetic impurity in their modeling were not incurring into error due to the approximation they used. Another important thing to note here is that the effect of the disorder strength on the spin relaxations measured. For SeO2, the spin relaxations are much smaller than that for HBN, since the disorder here is more strong. The impurity couples more strongly to the band states and is able to relax the states more efficiently. Another important thing to note here is the fluctuation observed in our data. For instance, the top curves here, the blue and cyan, and here, spin relaxation times obtained by taking the median of our distributions. So you can see that for the HBN there is not the difference not significant, but very significant between these curves, but for the SCO2 it is very different, indicating that the outliers should be dictating the behavior of this median. We can see this more clearly here on evaluating the distribution for the spin relaxation time for SCO2, where you can see that the median for the histogram for each energy, the median essentially is close to the values predicted for the graphene original theoretical prediction, which were the order of 1 microsecond, and that the mean is extremely dominated by those values in the tail of the distribution. And you see a very large variation here. So this means that you have more rare configurations that determine the spin relaxation in the system. When we go to the HBN, we see that this effect is much less pronounced since the system is much more homogeneous. In principle, our results were performed for a charging energy of 10 milli electron volts, and those were the results obtained, which is much less faster than the experimental results, which would rule the magnetic impurities as the one determining the spin relaxation in graphene in HBN. However, if we increase the Coulomb energy for the system, we see that for U value of the order of 1 electron volt, this could still be a significant mechanism for the system. And we can still rule out the magnetic impurities as generating spin relaxation in HBN. We also observe a reduction of the spin relaxation for SCO2 with the increasing of the charging energy. Another comparison that we performed was to observe what would be the spin relaxation time for hydrogen model. We also, here is the results, where we also had the results for R equal to 0, which means to confine the magnetic moment only to the hydrogen site. And we can see that the results very similar to the one obtained for our vacancies, indicating that whether you're on a system with vacancies or a datum, the results for the pi-like magnetism for the spin relaxation should be the same. So, one important insight of the results obtained, if you remember the STM results shown earlier, that when you put a hydrogen atom in an opposite lattice where you previously have one hydrogen magnetic moment, you can turn off the magnetic moment that was in the system. Since you observe that there are some configurations that can be more efficient to relax the spins in graphene, it can occur that when you increase the amount of hydrogen atom in the system, you are turning off some of these impurities, and you might be turning off some of the most efficient, more efficient impurities, and eventually increase the spin relaxation as the one proposed here by the experiment. This could also shed some light on the puzzle mentioned by Dennis on whether the spin relaxation in hydrogenated graphene is originated by the induced spin orbit coupling or the induced magnetism, since once you observe this increase in this spin relaxation due to increase in the hydrogenation density of impurities, this can be originated by turning off the magnetic moments, but not by the spin-orb coupling, since you will turn off the magnetic impurity, but will not turn off the spin-orb induced by the deformation of the lattice. So, in my conclusion, we could derive the microscope approach for calculation of spin relaxation times, which allows to understand the dependence of the spin relaxation time on several parameters, as the charging energy, the strength of the disorder, the resonant position, the degree of localization of the magnetism induced by those impurities. Use experiments inferred parameters which give estimates in tau s with good agreement with experiments. The results suggest that the pi magnetism is the key player for the spin relaxation in hydrogenated graphene and not spin orbital, and also offers an alternative proposal for interpreting the enhancement or decreasement of spin relaxation time in hydrogenated graphene. So, thank you for your attention.
Thanks, Vladimir, for nice talk. Didn't you try also to look for the RKKY interaction and the ordering of the spins as a change?